Jess Riedel and I swapped the order of our talks at the last minute because we thought I was going to introduce some ideas that he was going to use and also some other ideas that he was going to explain why they were wrong. And so that doesn't work very well in the other direction. So I'm going to go on, and it'll be a little bit repetitive of what I said at the beginning as the introduction as to what kind of questions are fascinating me and what I want to understand more about. I think a lot about the relation between dynamics and computation, and I want to try to say what I mean by self-organization, or what we mean, and then it has to do with evidence in the present state of a thing, of what its history might have been. And I will discuss true and false evidence in the problem of the Boltzmann brain. And then finally I'll talk about Wigner's friend in the problem that connects to quantum foundations, of what it feels like to be inside an unobserved superposition, which is pretty much what we're all doing right now. So back to this model, I was explained that this is a classical model which has this process of appearing to develop a complicated structure in the short term if you started from a low entropy initial condition, and then it equilibrates well, let's say in more detail that we've got this computerized Occam's razor, and this was an image suggested to me by Gregory Chaitin. That is, the monkey doesn't type at the typewriter, it types at a universal computer. And this is this distribution of all outputs of a universal computer on random input, or what I think Levin calls the universal semi-measure, or the a priori, it's the a priori probability, except it's not normalized because of, properties that Peter will talk about in computability. It sort of has a picture of everything that can be shown by deductive reasoning or numerical simulation. And this is how I suggest this idea of logical depth, which I've pretty much gone through before. If you believe the shortest program is the most plausible, then you have to believe that its runtime is the most plausible history of the thing. And for example, so therefore you're going to get an orderly sequence is shallow because it can be rapidly computed from a small description. A random sequence has high Kolmogorov complexity, but is also shallow because it's essentially its own most concise description. And as trivial semi-orderly sequences are shallow because you can rapidly compute them from their algorithmically random parts. So now we have this problem of this phenomena that I said before, which is that apparently the thing gets more and more complex in this precisely definable way for a while, but then eventually, but it takes exponential time, becomes not complex or not deep, because the evidence for its having been connected with that special initial condition has become obliterated by the very long time it took to get there. And I would be very interested in hearing how this kind of approach, where we consider the time and also the randomness, will compare with the things that you're going to talk about, Adam. And I said, why is the true history no longer plausible? And that's because to specify exactly how far you have to go back along the trajectory to get to the simple initial condition itself takes too many bits. Now I was when I was looking at the kind of complexity that you people at Stanford talk about, I was a little disturbed when I was there a couple of years ago that you were mixing gate complexity with which is a kind of complexity that involves both descriptive resources and dynamical resources. And I think it's important to know how much description and how much dynamics you're considering. So I suggested pointing out that, or suggested that the layout of the gates should not be used as a descriptive resource. It should just be a dynamical resource. And the way that's usually done in gate complexity is to say the layout is entirely specified by a simple Turing computable function. So I think that's a problem that's gone away. But now we have some phenomena that I used to believe in that I'm not so sure I believe in anymore. And certainly we see in the world, in the world at thermal equilibrium with local interactions, the correlations are generally local and short-ranged and mediated through the present. So in a system at equilibrium, if there is, I don't get long-range correlations between the state of the air here and the state of the air there, except mediated through what's in between. But in a system that's out of equilibrium, like the one that we're in here, we've got all these long-range correlations. For example, the DNA in all of us is shared, a great deal of it, not because we've directly interacted, but because we're descended from a common ancestor. And I took an example here of two coins which both have a picture of Queen Elizabeth on them. And they don't have that correlation because they were ever in contact, but actually for something that happened several centuries earlier, a different Queen Elizabeth. So I gave this model or this idea of allowing a system that is full of the kind of interesting complexity that we have, like in the world, allowing it to equilibrate. And I think both in the quantum state sense and in the classical state, it would become boring. And I would say would lose even its, not only would it lose its logical depth, it would even lose its classicality if you allowed it to equilibrate, because the quantum state of this kind of system is typically, if you let the dynamics run for a very long time, it's typically highly entangled and have only short-ranged correlations. So what is the connection between equilibrium and complexity? Are thermal equilibrium states, is there any way for them to avoid being boring and shallow? Now there's a principle in statistical physics and thermodynamics called the Gibbs phase rule, and it's exemplified by the phase diagram of a material like water. And that is, if the state of it is determined, the equilibrium state, by some independent variables like pressure, temperature, magnetic field, strength of some coupling constant, in general, if you choose them arbitrarily, you'll end up in where there's only one stable phase. And that means then that this system will not work as a reliable memory. It forgets its initial condition and eventually settles into the state of the Gibbs phase of lowest bulk free energy. And the reason that really happens is that as you vary some field or parameter, one Gibbs phase or another will have the lowest free energy, and if you wait long enough, the metastable one will decay to the stable one, and so it's a rare coincidence for two phases to have the same bulk free energy. And for that reason, metastability is the common feature. So if we take a credit card, for example, and leave it for a very long time, in the Earth's magnetic field, it will forget what's stored on it. Now, there are models which I think Peter will talk about. Maybe, will you talk about them?
I wasn't asked, I was asked to talk about computational complexity.
Well, yeah, okay. Well, he knows about them, so you can ask about them. Maybe I'll talk about them. There are models where if you have a dissipative process, that is one which is not does not obey detailed balance. If you wanted to make it happen physically, you would have to plug it into the wall and take away the waste heat. And these things can exhibit a stability that normal thermodynamic phases don't have. That is, if you put on a small perturbation, it will nevertheless be a stable memory, despite absolutely stable rather than metastable. But I'm beginning to doubt this in a way that I guess gives me hope. That is that that there are models in quantum memory, and in maybe even David Poulin is going to give a remote talk about a model that he's been considering, which is a classical three-dimensional model, which appears to have this stronger kind of stability. That is, a stability, an ability to resist a lifetime for both states of the memory that increases with the size of the system without bound. So the bigger the system you make, the larger, the longer the time the memory will be preserved. Whereas in an ordinary metastable system, like let's say a piece of supercooled water, there's a definite nucleation rate for every amount of supercooling of it, and you can't make the thing more stable by making it larger. So I think one thing I'd like to understand is, can you get stable memory quantumly? What does it take to get stable memory and a stable record of a computation, which perhaps a logically deep state, at equilibrium at positive temperature? The Gibbs phase rule said you can't do it, but I think the Gibbs phase rule maybe have exceptions. I believe it does have is not really true for some quantum systems. It may not even be true for some classical systems. And there's an old paper I wrote with Jeff Grinstein, in 1985, made this comparison by saying that if you have a dissipative system, of course a dissipative system doesn't have a well-defined free energy, a dissipative system with local interactions. But you can always embed a local probabilistic process whether it's dissipative or not, in a locally interacting history. That is, where the state at time t determines the probability for the state at time t plus 1, and you use the transition probabilities, regard them as the exponentials of energy of interaction between the time slices. So this is what we could call a transfer matrix way of looking at the history of something, and just think of the history as a static state of a system in one larger dimension. But that static state, because of the normalization constraint, the fact that there is always one future for each present, means that no matter how you vary the dissipative system's transition probabilities, the free energy of the d plus 1 dimensional system is identically the same. So you get this thing in a d-dimensional system where, as you vary the field or parameter, if it's a